Alright, we're getting to some of the much more difficult advanced problems. Here's problem 7 from the 2021 Fall AMC 12A. This was problem number 21. Let ABCD be an isosceles trapezoid with BC parallel to AD. So kind of weirdly drawn here, but yes, these are parallel. And AB equals CD. So this is a typical isosceles trapezoid. Of course, we have these. Points x and y lie on diagonal AC with x between A and Y as shown in the figure. And suppose AXD equals BYC equals 90 degrees as shown in the diagram. AX equals 3, XY equals 1, and YC equals 2. What is the area of ABCD? It's actually one of my favorite types of problem. We have like a geometry problem, and then we have some sort of maybe we have like a trapezoid, we draw the diagonals, it gives you like the area of like 3 of the numbers, and then you have to figure out the area of the 4th, right? This is a very similar type of question. I really like these geometry sort of puzzles. In this case, we do have a lot of ideas that can come to mind that come from the fact that this is a trapezoid. In particular, we also have a lot of right angles, so that's also very nice. With right triangles, we have a lot of information. Let's take a look at this diagram. Let's redraw it so that it's easier to see the sort of symmetries of the trapezoid. In this case, I'm just going to rotate it so that we can see the parallel lines, I guess, better visually. So we draw diagonal AC, and then we draw perpendiculars from the other two corners. And we're given that this is 3, this is 1, and this is 2, right? Okay, cool. Yeah, so now we have a lot of information. One thing we can tell is, well, these are parallel, so that means these are equal angles. Oh, but we also know that these are parallel because they're both perpendicular to the same line. So we have even more equal angles. I guess we already knew that these were equal. So we have these two triangles that are actually similar. And, right, that is actually really good information, right? In particular, we have this. We've just proven that this triangle ABY is similar to so ABY, or sorry, BYC. So this one here is similar, BYC, to DXA. Right? One is just sort of like a rotated 180-degree version of the other scaled up. And so we can see this sort of, I guess I drew it wrong. Yeah. Okay, so this is supposed to be, wait, I think I did this. Okay. It's just swapped because of it's like less it's a skinnier trapezoid, but you get the idea. These two are similar due to these parallel lines. Okay, so we have two right triangles that are similar. What else do we know about them? Well, we know that these two sides are corresponding. CY and AX here are corresponding, and they're in the ratio 2 to 3. So that actually tells us that, in fact, that these two BY and DX, which are also corresponding, are in the ratio of 2 to 3, which we can call them 2x and 3x, and similarly we can call this 2y and 3y. So we can actually figure out, okay, from this, how can we figure out the area of ABCD? It still seems kind of out of reach, especially because we just don't have a lot of other information. Well, we can figure out, some sort of nice relationship based on other properties of the isosceles trapezoid, right? We still haven't exploited that sort of isosceles part of trapezoid. Actually, we know that it has this sort of symmetry here. In particular, we have AC drawn, but we should actually draw BD. Maybe that should help us, right? Because we know that two diagonals in this symmetric shape have to be equal. And in particular, we know the length of AC is 6, so BD equals 6. Hopefully this should help us progress. So in particular, we also haven't used the fact that these are right angles yet. So if we call our attention to this sort of new triangle is drawn, if we call this point in the middle Z, then BYZ and DXZ are similar, and we actually know that the ratio of their lengths are 2x to 3x, so this is actually still 2 to 3, right? We can think of it as sort of this triangle BCZ over here and the corresponding DAZ, right? But we can see that we have actually more than enough information to now finish the problem. We know that we have some like interesting lines here. We know that this is 2x and this is 3x. These are right angles, and the total length of the diagonal here is 6, and the total length of here is just 1, right? So how do we actually solve, I guess, for x? And if we solve for x, we can actually solve for everything else in this trapezoid. So basically, we're just trying to solve for that specific value. One thing we can do is just, write them all in terms of ratios, right? If this, since these are in 2 to 3 ratio, we know that 1 is split into 2/5 and 3/5. Similarly, we can split the hypotenuses into, 2/5 of 6, so 12/5, and then 3/5 of 6, or 18/5. And then we can just solve for x this way, right? One other interesting way I'd like to point out, and this is the way I sort of thought about it initially, we can see that we can sort of drop this sort of middle length here down to the bottom, and we can see that the total length from top to bottom is just 2x plus 3x here. So we have this is 5x, and the hypotenuse is 6. So we can actually just solve for x this way. Either way, I'll use this way because it looks cooler. 5x squared plus 1 squared equals 6 squared by the Pythagorean theorem. So we get 25x squared equals 36 minus 1. So x squared equals the square root of 35 over 25, or just root 35 over 5, where the 5 is outside of the square root there. Okay. With that in mind, let's now return to computing the total area of the trapezoid. Let's go back. So now we know the value of x, so we actually know basically everything, right? Remember that x equals root 35 all over 5. In this case, one easy way to compute the area is just noticing that ABCD is composed of two triangles above the middle diagonal, so ABC and ACD, right? That diagonal being AC. And we have heights specifically drawn, right? BY and DX in particular. And if you remember, those lengths were 2x and 3x. So our answer is just 1/2 times the base, 6, right? AC equals 6, times 2x plus 1/2 times 6 again, times 3x for that bottom half. In other words, 1/2 times 6 times 2x plus 3x by the distributive rule. Okay, well 5x is root 35, so the total area must be just 3 times root 35. And that is our final answer.